We are now in the fourth phase of homogeneous transformation matrix presentation. In this phase, we are interested in running those MATLAB scripts that we have developed and discussed in our presentation. Here, I'm presenting 4 different scripts. I'm starting with MATLAB script 1, and in this area, as I've told you before now, it is about two-dimensional object. The point is located at point P, and point P has coordinate of 3, 4, and just because we are presenting the point, the point, which is an object here, as a vector, therefore we make use of 3 semicolon 4, and we close the bracket, and we terminate the vector by making use of semicolon. This particular vector has 2 rows, 1 column. Row 1 contains 3, row 2 contains 4. That is, in this location, P function of 1 contains 3, P function of 1 contains 3, P function of 2 contains 4. That is, and I've told you, when you move from the point where x is equal to 3, and you move from the point where y is equal to 4, the point where the two try to intersect forms P. And we are now interested in translating point P through 2 units away for x. We are moving point 4 minus 1 unit away, and therefore to do that, this particular section of our discussion, what we are seeing here represents this section represents generation of the object. Then, for us to be able to move the object that we have been created here to 2 units away in direction of x-axis and minus 1 unit away in direction of y-axis, we are now making use of homogeneous transformation matrix, which is covered here. This is a homogeneous transformation matrix, as we have stated in our discussion before now. This is a row vector, which I call scaling factor matrix or scaling factor vector, and these two columnar vector here, these two T1 and T2, they form what we call columnar vector, and the two denote translation vector, whereas what you are seeing here from here to this particular area without T1, that is 1, 0, 0, 1, they are identity matrix representing rotation matrix. And for us now to be able to translate point P using translational vector, we need to work on point P so that it has to contain 3 rows, so as to be able to have 3 by 1 matrix or 3 by 1 vector. Now, to have that vector, we have now included another row. Row 3 contain 1, whereas P, this particular row, contain 2 rows. P contains 2 rows, that is row 1 which contains 3, row 2 which contains 4, and row 3 which contains 1. That is, why are we doing this? We are doing it in such a way that we can multiply 3 by 3 homogeneous matrix with that of 3 by 1 homogeneous point. So having done that, we can now carry out our translation by multiplying transformation matrix by P of homogeneous, the position of homogeneous, that is point P that has been added with SK1. Having done that, we are now ready to display our result. And this is the result, that original position that we are displaying using this command. That is, for us to be able to know what we are displaying, what we are writing here is going to appear like this. That is original point colon. Then the content of my P is now going to be displayed. Is now going to be displayed using display P, but we use prime so as to be able to read the display in row, not in column. Because if you don't transpose, what you are going to get will be in vertical, which is going to be with that is, we are going to have what we are going to call if there's something like a prime here, we are going to have columnar vector. But with prime, you are going to have a row vector. Then for the translated point, the point that we have been translated, haven't moved, in x direction 2 units away, in y direction -1 away, we are not going to get new point entirely. Then we want to show that the point is translated point colon. That one is going to appear. The content of this location here is not going to be what this one is going to display. But we want it to display it not in vector, not in columnar vector, but row vector, and that's why we put transpose here. So I'm now running what you are seeing here. By the time I run it, you now see the result. So this is the result. That is, this original point 3, 4. This is coordinate of the original point, and this is coordinate of a transited point. After 3 has moved 2 meters away, or 2 units away, we got 5. When this moved, when 4 moves -1 away, 4 minus 1, we have gotten 3, and this is what we have obtained. And this is our example 1 when I was presenting the lecture. Then for us to be able to see how to see the point, original point, using a marker, to see the translated point using a marker, then to link the two, because this is a vector, and I've told you we now make use of a command called quiver, and what quiver is going to do is just to move this point, fire this transition point. By the time we do that, the thing is going to move, is going to connect this to this, and that is what we are having here, what we are having in example 1b, the second example that we try to carry it out in that particular environment there. Let me now try to see, let try to run um, uh, or let try to run that information that has a quiver. So this is from here to here, this is what we have done. We have not been able to realize our third objective. The third objective happens to be to visualize, and we are now visualizing because what we are seeing here happens to be for generation of the object. We generated object here. We use homogeneous transformation matrix here, and up to this area, but we just see the point. We have not been able to see the point visually. We have not been able to visualize the two points, that is original point and the point where the original point has translated to. So let us now see. For us to be able to visualize that, then we are making use of all the statements that we are having here, and you need to understand the syntax of everything there. Then we are interested in locating the original point and the transition point in one single window, in one single figure, and that's why you see figure here. Now, to plot two-dimensional plot, you need to indicate the point denoting x point, and since we are dealing with a point p, the first p function of 1 is indicating x, and p function of 2 is indicating y, and the word plot we plot the two, is going to identify where x and y intersect. So now, to indicate the color of the plot, we use a blue color, and that is what this one is indicating, b. And the marker is represented using O, and the size of the marker, which is O here, is 10, and the thickness of the hole is 2. That is what this one is representing. But sincerely yours, if you don't know what to write here, just leave it. The system, the MATLAB is going to put appropriate value there, so as to be able to differentiate what we're having here from here. Then this statement here is telling us that this plot should be on. It should not be clean off. And then we are going to place another plot on this particular figure with this one standing without going nowhere. It's going to remain there. Then we are now bringing in the point P that has been translated. I've told you are going to see the point X, and this point X of a translated P, and this is Y. And here we are representing this point where P and this particular tries to intersect, where they tries to meet. Then here we are making use of a red color to represent it, and marker that we are using is X, and the size of that marker, the size of that marker that we are talking about happens to be the marker size, how the S is going to be. Then the thickness of the X is now going to be the length width of 2. Then but to now try to indicate the direction that quiver, I've told you before now, it represents the direction of the vector. Then the direction, for you to be able to indicate direction, there must be a line with an arrow. And to indicate that one, you are going to say that it should, there's need for you to indicate the point where the thing is starting from, and that particular point is point P. And point P is made up of two different, it's made up of X and Y. That is, point P is X, Y, where X is P function of 1, Y happens to be P function of 2. That is, the content of Y is going to be here. Then this is the direction. That is, the arrow with, the line with an arrow is going to move this distance away, for X, for Y, and it's not going to connect with an arrow with, just because of this command quiver, and you close under normal circumstances, you now try to do that. When you now do that, you specify the color. The color that you are using this time around is color K, and the length of the line width of the color K is 1.5, and this is axis. You want the axis to have from in x-axis to start from 0 and end at 6. The x minimum is 0, x maximum is 6. On the y-axis, y minimum is 0, y maximum is this. But this one is not necessary, or you can use axis equal. If you do that, the system is going to know that it's going to apportion appropriate axis, to your plot. Then grid, you want to see the grid, the lines, so as to be able to interpret them. And after doing that, there is need to differentiate to identify the original point and the transited point. Then you write the name you wanted to give to this one. That is, when you write legend, the MATLAB package knows that under normal situation, the original you write here is legend for this plot, translated is legend for this, and the transition vector is legend for quiver. And this is the title of the work of the plot. The 2D, you say 2D, it must be inside inverted comma, the way the thing is. And you start with a coil bracket, you close the coil bracket, and you terminate with a semicolon. Having done this, we are now going to run. We are now running what you have here. And now come to this area, I put my cursor, then I put this. So then this is what we obtained before now. This is what we obtained. Then it's going to generate a curve, and this is the curve. So this is the curve. It has been able to tell us the curve, and it has been able to tell us, as you can see it on your screen, this is the curve. That is, this thing is trying to tell us that this original position with this zero marker, and the zero marker has a blue color, and this is the where this point has moved to this area, and we use x to represent transited position. And with use of quiver with the color black, we have this line, and that is what we have been able to obtain. And I've told you that the original point is, x is 3, y is 4, and we now meet here, and that is why we obtain this particular position that we are seeing here. This is the position that we are seeing there, and you can see that under normal situation, this is it. This is what we have. This is 3, 4, and the transited line is 2, -1, as we have seen here. And when you get to this one, then you are going to see coordinate here. The coordinate at this point is happens to be, that is here. You will see that x is equal to x is 5, whereas this one is 3. That is, by the time we try to make use of transitional vector on this, and that's why we obtain the value. And that is a sample of point that we plotted. We plotted the original point, and we plotted translated point, and we achieved this aim. And we show the legend, for the original, for the translated, and for the transitional vector or translation vector. And that is that. Having done that, we are now going to the second experiment or second simulation that we did when I was doing the presentation. And this is it. And this second presentation that you are seeing there happens to be a cube, and a cube happens to be three-dimensional object. And the representation of three-dimensional object, when you look at the vertices of cube, it has 8 vertices, and each of the representation of vertices, as I've stated to you, is what you are now seeing here. That is, and for you to be able to know that it is a three-dimensional object, this is a complete row 1, telling us the coordinate for x. This row 2 telling us all the coordinate that make up 36 for y, all the points for z, because for the three-dimensional plus we are going to have x, y, z. That is, the first point is when x is equal to 0, y is equal to 0, z is equal to 0. The second point is when x is equal to 0, y is equal to 0, z is equal to 1. And the last point is x is equal to 1, y is equal to 1, and z is equal to 1. These points generate all these points that we are having here generate what we call a cube, and this one try to give us 3 by 8 matrix. And we are now translating in our work, instead of 4 here, we are translating to, that is, we are moving one away. No matter their position here, we are moving them 1 unit away. The position of y, no matter where they are, we are moving them 2 units away. And for z, we are moving z 3 units away. And we have now been able, to generate cube. And from here, we are preparing, to be able to have homogeneous transformation matrix. And to do that, we need to denote translation vector, and this is it here. We have generated that translation vector that's going to have the dimension of 3D, which is going to be 3 by 1. And for us to be able to have the matrix that is n by n by n by n by n, but don't forget, transformation matrix is going to have, for 3D, it's going to be 4 by 4 matrix. To generate 4 by 4 matrix, we use I function of 4. I function of 4 is loading this variable location t, variable location t with identity matrix of 4. But you see, the fourth column of identity matrix supposed to contain t, which is translational vector, and that one is going to be 1, 2, 3. Then the remaining one is going to be at row 4, column 4. Therefore, we are forming identity matrix and translation matrix and scaling factor vector. Now, that is t here is trying to say that 1 by 3, the whole of 1 by 3 matrix is going to be retained. But column 4, you retain column 1, column 2, column 3. But column 4 must be occupied by t, and that is what this one is trying to say. And in this column 4, we are going to occupy only 2, 4 elements, what we call a cell that is named 2, 4. 2, 4 is going to have, 1, 4 is going to house 1. 2, 4 is going to house going to house 2. 3, 4 is going to house 3. Whereas 4, 4 is going to house 1 that is already there before. And that is how we form our transformation matrix here. And the essence of transformation matrix, in order to translate it from one point to another, is just to multiply, to carry out matrix multiplication, together with the object. And the object, translation matrix that we have here, homogeneous translation matrix that we have here, has 4 by 4 matrix, whereas this one has a 3 by 8 matrix. For us to be able to carry out matrix multiplication, this cube matrix must be 4 by 8 matrix. To make it 4 by 8 matrix, therefore, there is need for us to create additional row. That is, that particular row will contain ones, and that is what this one is trying to say. And we call this one cube homogeneous. We make it to be aligned with the transformation matrix that we have formed here. And therefore, we say this particular cube, under normal circumstances, you create ones. Let the one, because this is a vector. and that particular vector has 3 by 8. Then the fourth row that's going to make this particular keep home to become 4 by 8 matrix, add this one to row 4, and one, what this one is going to contain is going to contain 1 1 1 1, the all element, 8 element that form the row. The row 4 is going to contain 1 1. Therefore, we have made keep, by tries to homogenize it, so that it's going to have 4 by 8. 4 by 8 we can now carry out what we call matrix multiplication. You know the rule of matrix multiplication. The number of elements in the row will be equal to the number of element in the column of what if you have a matrix multiplication b, a must have the row in a must be equal to the row, to the column in b for the matrix multiplication to happen. And this is what we have now been able to do. We have now been able to to translate the keep to this area using homogeneous matrix that we are seeing here. And we have now been able to move homogeneous matrix, but we need to see it. For us to be able to see it, then we are going to put everything in a cube, and that is what we have now been able to do. Figure. Everything is going to be here. And since we are having two plots, one for the original cube and one for the transited cube, then we are now making use of subplot command. And I've told you subplot. Here I'm creating one row, and the row is going to contain 2 columns. The first column is going to house this cube, and then when you look at this area very well, we are using plot tree. Since we are carrying out 3-dimensional plot, then you need to tell the MATLAB package of the compiler that I'm interested in 3D, and that's what this one is all about. But for 2D, you don't need to put anything there. You don't need to put anything in that particular area. Then this one is trying to represent the whole of row 1 in a key, because you need to represent, this is representing x, all the points, all the 8 points in row 1, tries to indicate x, and this one indicate y, all the elements in row 2, and this all the elements in row 3, which happens to be z axis. Therefore we are now having Cartesian coordinate. Then here, having done this, then we need to indicate the color of each of the vertices of all the vertices using color blue, and we are making use of a hole to indicate that. Then the title of this plot is original cube, and we use axis equal, as I've told you before now. That is, leave the dimension of the axis, x minimum and x maximum, to MATLAB to do, because so that you think about another thing entirely. Then you want the grid to show, and you are telling the system, the MATLAB package, that you are doing 3-dimensional plot, and therefore fill 3-dimensional plot. This is what that one means, so that it will not give you 2-dimensional plot. That is what we are going to do. For the second plot, which happens to be what we are, the cube that has been moved from one point to another point entirely, that one is going to occupy the column 2, that is row 1, column 2. That is going to be there, and there is more or less is the same thing with what we have done, but the x here, the whole of the x is going to be here, the whole of y is going to be here, the whole of the point, and these are the point that is going to the system is going to denote, and it's going to sketch these 3 points using all these three, this one contain 8, this one contain 8, this one contain 8, and all these points are going to be represented using red color, and it's going to be the O2. And other ones are concerned, the title is transited cube, and fill 3 and let it remain, so that because if you don't put grid on, this one will go, only this one will be there, and that is that. And when we now run this, what you are seeing here, this is what we are going to obtain. Yes, I'm waiting. We are waiting for that. So this is what you are going to see, and you have seen this is original cube, and this is transistor cube, and you can see we move x. This is x. It's equal x. We move it away by 1 unit. We are now having 2. We are now having 2. This is a line x again in this area. We move it by 1. We are now having 1 5. Let us go to, this is a set that we are seeing. We move set by 3. We are having 4. This is set. We move it by 3. We are having this, and this is the y. This is why we move it by 2. Or translate it by 2. We have 2.5, and that is what we are talking about. And as I've told you, by the time you place your cursor here, this one is going to show you the content of everything here. That is the coordinate that form that, and that wants to show that at that point entirely, our x is 1, y is equal to 0, z is equal to 0, which is one of the coordinates or something here. When you come to this area and you put your cursor again, you are going to see that that particular area, at that area, y is 1, x is 1, y is 1, z is equal to 0, and that's what formed that. But this area, everything is 1 1. At this area, we are having this one is that is, in this area, z is 1. At that point, x is 0, y is equal to 0, and that is how we obtain all those things. So that is the plot of three-dimensional plot, or three-dimensional object for you. And by the time you change the coordination here, you will see that all these values, they are going to change, telling you that they are now in another location, and that is that for you. Then, having done that, we are going to another MATLAB script that are explained in that particular, in our PPT, in our PowerPoint presentation. And here we are generating 2D, two-dimensional object, which is the triangle. And in two-dimensional triangle, we only need element for all the vertices, for all x-axis, in the x-axis, and these are the 0, 1, 0.5, and this is y. For vertices in y, these are they, and this one tries to give you 2 by 3 matrix. And what are we trying to say? At this point, when x is equal to 0, y is going to be 0. Then the area is going to be marked. At this point, when x is equal to 1, y is equal to 0. Then we are going to mark that. At this point, when x is equal to 0.5, that is in between 0 and 1, 0.5 here, then y is equal to 1. Then that one is going to go up. Then at the end of the day, then we need only two lines, yes, this and this. And therefore, the third one forms what we call a triangle. But for us to be able to, that is, we have not been able to generate triangle, as I've told you. We generate triangle, and for us to be able to move it, then we need to declare, translation vector. This is our vector. This is our vector. Our vector in normal in the presentation is 0.5. Let me change it to 0.5, and this one 0.5 again. I will change it to 0.5 for uniformity's sake. And here, since we are doing what we call two-dimensional transformation, then one thing you can do here is just to create 2 by 2 matrix. That is what we call our original identity. Do you get it for now? So that then we had the transistor vector there, the t, and t is having 0.5. That is, this one is going to contain t function of 1, t function of 2. Then when you now try to do that, this one is generating 2 by 2 identity matrix, and we are now adding what you have here to that. Then to create columnar vector, we are now adding this. Then we have gotten 3 by 3 that's supposed to be for two-dimensional plot. Then for us to be able to be able to carry out matrix multiplication of this triangular object that we have done. But this triangular object is 2 by 3. We need to make it you need to make it 3 by 3, so that at the end of the day we can now be able to multiply 3 by 3 matrix that we have been able to obtain here by 3 by 3. So at the end of the day, that is why we have added this one there. The one here is going to occupy the third row. The third row, one is going to be here, one is going to be here, one is going to be here. And when you now try to do that under normal circumstances, we can now carry out matrix multiplication here, and we can now plot our curve. The same thing that we did. The only thing that different here is that we fill, when you are going to fill an object, you want it to have a color. Triangle 1 and triangle 2. This is the x and this is y, and you are drawing the two lines that form that particular triangle using what we call color blue, and you are now trying to paint the triangle that you have formed here using blue, and the face, that is face that you are doing, and the thickness of the line is going to be 0.2. But for the translated triangle, what you are trying to do here, you are making color red so as to be able to differentiate. The thing is going to move 0.5 away, and by the time we try to run what we are having here, automatically you are going to see what you are going to have. And what we are having now happens to be what you are seeing now. This is it. This is what you are seeing. This is what you are now seeing. What you are seeing here, this is the original matrix with the color blue, or the translated with the color red. We have moved original to this area 0.5 away. For instance, x is 0 here and y is 0. When you get to this point, you will see that x is 0.5, y is 0.5. And when you get to this point here, x is 0.5 and y is 0.5. Y is 1. That is that. Y is 1. When you get to this area, we have moved x 0.5 away. Therefore, here we are going to see that x is going to be 1, y is going to be 1.5, as you can see. And the same thing here, x has moved, for 0.5 away. We are now having 1.5, and y is now 0.5. And that is presentation of two-dimensional plot. And what you see here, when we were presenting three-dimensional plot, under normal circumstances, we put 3 here. There's two-dimensional plot, you don't put anything. But that one reminds me that under normal circumstances, by the time you have another object entirely, like a cylindrical object and spherical object, we normally use another thing entirely. And by the time we want to know it, we can try to come for help, and help is going to tell us the type of plot we are going to use here. Now, and having done that, we can now go to the scenario problem, which is this one. Scenario problem, which happens to be a robot. The robot, we represent the robot with a point, and that particular point is point A, and point A using coordinate geometry 2, 3. And just because the object is supposed to be a vector, because so as to be able to do the needful. Now we have 2, 3. That is the position of the robot initially. But thereafter, they told us that the targeted position is B, which is 6,6, but I've just used 6,6 here. I've used 6,6 here. Then that is targeted position, and the targeted position under normal circumstances, we now try to say that when an object gets to the targeted position, it finds out that there's an object nearby, and it now the robot needs to change the direction so as not to hit the object, the doors of not to hit the obstacle. Then when it now try to do that, then the translation to that particular area is given to us here. And for us to be able to make use of a transformation matrix, we need to find translation vector. To get the translation the first translation vector, the translation vector is going to be this minus this this minus this, and that is what we are having here. Transitional factor 1 before before you now change to another position entirely using this particular transition factor. The first transition factor is this. The second transition factor is this. For the robot to be able to get to this point, it's going to it's going to make use of transition factor here and transition factor here. We need to find the product of that, and that is what we did here. The total transition factor is T2 times T1, and this is what we are going to use to move the object here to C position. So then, the transition factor 1 under normal situation, since we are dealing with a two-dimensional object, the 1 0 and 0 1 form what we call our identity matrix, and our translation factor is formed by T1 factor 1 function of 1, which is this one, T1 function of 2, that is the position y of this one and position x of this one. And for this C, that is final the transition factor, then we use T2 factor of function of x and that of y, and 0 0 1 happens to be the scaling factor in order to make transitional factor to be 3 by 3, and for us to be able to, what we are obtaining here happens to be 2 by 1 factor or 2 by 1 matrix. Then for us to be able to carry out matrix multiplication, it must be 3 by 1. To make it 3 by 1, what we did is just to add additional row, and that row is going to contain 1 row. That is, our A is 2 3 1. The 1 is now added here. Then we have now gotten 3 by 1. 3 by 1 can be multiplied by the transition, any of transitional homogeneous transformation matrix here, and that's what we have done here. That is, at B, you make use of homogeneous transformation factor transformation matrix that we obtained here. We multiply it by this, and final, the total of a transition homogeneous transformation matrix that we obtained, you multiply it by homo that we have now been converted to 3 by 1. And after that one, we need to visualize what we have done. Then you make use of everything that we have done. That is, for 2D, you need x for A1, you need the x for A, y for A. Then this is x, this now represent y. For point, we are for the point, to indicate the point before tries to take another direction just because of obstacle. Then is B1, is B, and B, this B1 represent the x, this one represent y. We draw this one by making use of color blue. It makes use of O, and the marker has the width of 12 units, and the thickness of this O is 2. And here the width, the color of xy is going to be red, and x represents a rectangular shape, and this is the marker for it, and this is the dimension, the marker size, and this is the thickness of the line that form that particular marker with this rectangular shape. And for the final plot, which happens to be the final position, for final position of the robot, then we use final. So that is, we use what we call green color, and green color we make use of this marker. This marker is a triangular marker, and the size of the marker is 12, so as to be able to be uniform with this, and the line thickness happens to be 2. Then there is still for us to draw 2 feet, the one from A to B and from B to final. And from final, therefore, we need 2 quiver. The first quiver is going to take x, x and y, that is the point where the thing is, and to move it to the point where the thing is going to take that another direction. We make use of this transitional vector that we have defined, and we use color black, and this is the width of the line, and under normal circumstances the width of the line is 1.5, and the maximum edge size is 0.3. That is the arrow. Then here for the quiver, which happens to be the point before the robot tries to take another direction so as to be able to avoid the obstacle, is happens to be the particular theta x for B, y for B, and this is a transitional vector defined, given to us, and these are the information that we need. Hem, this is another color entirely, and this is the width. The line width is 1.5, and the size of the arrow is 0.3. And having done that, we can now, access equal, so that you don't bother yourself giving x minimum and y minimum. You can leave all these things. The system will know what to do. But grid on, in order to see the grid, then the legend for start of, you are saying start of A, start of, because you are in the number of a plot that you are going to have there is going to determine what you are going to have. Because here we have 1 2 3 4, 1 2 3 4 5, and you can agree with me here. This is it. The first legend is for this plot 1. The second legend is for this. The third legend is for this. The fourth legend is for this. For the fifth one is this. That is, the number of legend is going to dictate what you are going to dictate here. And the title of this work is robotic navigation part, or robot navigation part. Now we are interested in writing text, at point A, and to do that, where A, that is, this is x and y for A. Then for you to be able to write text there, you wanted to write the value a 2, 3. Then you use the word text. You open a bracket and you close the bracket, and to indicate x, because the x here is known as a function of 1, y here is known as a function of 2. But in order to not to write at the point where you have your marker, then we try to reduce the thing to come down. That's why minus 0.5, and minus 0.5 away from that. That's where we are going to have this one. The same thing for B, but we move the B a little bit up, so that the thing will not be written, at the area you have your marker, and you are going to write this value there. And the same thing here, that is for the final up, and this, that is, you are, a little bit below where the x, where you have your marker here, you are going to write the value that is generated here. That the value generated here for the x, the value generated in this particular area. Instead of using this, you can just use display, and it is going to display it here. But all those things are going to be inside text, and the text is going to appear. Let us now run it, and let us see what we are going to obtain. And we are now running, and we can now see what we are going to obtain. So this is what we obtain. That is, you see, this is the starting point. By the time the robot gets to this area using rectangle, which is x, color red, then the robot believes that there is an obstacle somewhere, and as a result of that one, it has to take another path, and that's why it takes another path given to us. We were given new translational and translation vector entirely, and that's why we are now here. All the legend given to us, they are now here 5, and that's why they are now here. And having done that, we can now try to, if we want, let us believe that we want B to be at this location here. Let's say we are interested in moving B from that area to this area. In this area, we are now having 6, and we have x is equal to 2. Instead of having 8 bracket open 8, 5, we can go to that area and do the needful. So let me just clean this environment, and we try to manipulate that area. I want to tell you that by the time we changed the coordinate, we are going to get another thing entirely, and that is what I'm interested in doing now. Now let's see. So this area where we have you see, for us to be able to have translation, that is b, I'm now changing. Let me see, oh no, let me generate it again. I wanted to see what we want to do. So that is the position of b here is C6, and let us even I'm coming. I want to move it to, let me move it to 7 2. 7 2. I want the B to be here, so that we are going to have another direction. That is, by the time we try to do something of that nature, let's see what we are going to have. Because we are experimenting, we are simulating, and we can do anything we feel like. Let's see. So I think I said 7. Let x be 2. X is now 2. Let me put this one to be 7. Do we have up to that? Yes, I've done 7. Let me save. Then we run. We will see the shape that is going to be different now. You will see the thing has changed just because we have done that. That is, by the time robot try to sense object, that is, it's going to change direction, and it has changed. And you see, with help of transformation matrix, we can with help of homogeneous transformation matrix, we can do and undo. Then in this particular lecture, once again, I've been able to carry the class along in such a way that they can now generate at least a point, a two-dimensional object, and a three-dimensional object. In MATLAB environment, after generating, they can try to make use of homogeneous transformation matrix to be able to translate the object they have been able to generate, and by making use of a plot command, and the plot command for two-dimensional plot, they can plot and visualize the object they generated in 2D. By making use of a plot tree command, they can generate, and fill tree, they can generate, they can fill the object they have generated, and by making use of homogeneous transformation matrix, they can move what they have generated. But for the feed, when we are having a point as an object, you can make use of quiver to be able to generate the direction of the movement of your point. And that is the end of my lecture for today. And this is this is phase 4 of what I started with. We are a MATLAB environment, and we have been able to demonstrate what we have been able to develop, and what I've been able to discuss in our presentation, in our presentation class. In our demonstration class, I have been able to carry the class along, and I have been able to, at the end of this particular lecture, by the time you do it very well, you should be able to generate a point, a 2D object, a 3D object, and after generating them, you can move them from the position where they are to another position entirely, and you can